In this video, I am going to cover hydrates. Hydrates are compounds that have water molecules basically stuck to them. They are not fully bonded to the molecule or to the compound. They're just kind of stuck to it. They tend to be ionic compounds, so they have a crystal lattice, which means they have like a certain three-dimensional structure, and the water is just kind of loosely stuck to it. It's not fully bonded to it. And you can tell that by the way we write it, which I'll go over in a minute. And if you take a hydrate and you heat it up, you can cause that water to be driven off. Basically, it's like the water's evaporating. It is leaving that compound. So in a question like this, it says a 3.0 gram sample of sodium carbonate monohydrate. So you can tell by the way it's written that, for one thing, the sodium carbonate, that is an ionic compound. You have sodium, that's a metal, which is Na, that's a +1. Carbonate is a polyatomic ion. It's CO3 with a -2 oxidation number. And the mono, they use that prefix, like the covalent prefixes. Mono means one. So it's saying there is just a single water molecule stuck to that compound. Now, if you heat it up, you will drive that water off, and you will get what's referred to as an anhydrous salt. It's just the hydrate sample we started with, but with no water in it. So what we want to figure out is how much anhydrous salt would remain and how much water was in the original sample. So first we have to finish writing the formula for the compound. So for the sodium carbonate, you crisscross the oxidation numbers just like we have been doing. So you get Na2CO3. And now with the monohydrate, you put a dot here and you write H2O. Now mono means one, but there's no need to put a 1 here. So we tend to leave it out. If it was dihydrate, you'd have 2H2O, or trihydrate would be 3H2O. But the dot that I put here is just basically showing you that the water is not really chemically bonded to this thing. The way we have to start this out is we have to figure out what percentage of this hydrate is actually water. So we do a percent composition problem. You have sodium. There's 2 of them, and sodium off the periodic table is 23.0. You multiply that out, and that gives you 46.0. The carbon, there is only 1 carbon, which is 12.0 off the periodic table. There's 3 oxygens at 16.0 apiece, so when you multiply that out, that gives you 48.0. Now, since I want to specifically know what percentage is water, I am going to keep that H2O all together. Now, there's no coefficient in front of the water because it's monohydrate, so that's telling you have 1. If we had dihydrate, for example, you would put a 2 here, or trihydrate would be a 3. But since this is monohydrate, we leave it as 1. Water off the periodic table is 18.0 because we know oxygen is 16 and there's 1 of them. Hydrogen is 1.0 apiece, but there's 2 of them, so that's 2.0. So you add that up. 2.0 and 16 gives you 18. Alright, now percent composition, just like in the other video I said, percents are always a part divided by the whole. Well, the whole is the molar mass, that 124.0 grams per mole. Right now, the only part I really care about is the water, so that is the part I'm going to divide by 124.0. Now, when you do that division, you get a decimal, and remember, for percent compositions for the percentages, I'm fine with you going to just 1 decimal place. So that becomes 14.5% H2O. That is the percent composition of water in that compound. Now this says if you have a 3.0 gram sample of sodium carbonate monohydrate, how much anhydrous salt remains. Alright, so that's what I'm going to start with. 3.0 grams of Na2CO3.H2O. Now, we know that 14.5% of that hydrate is water. So if I want to know how much water is lost, for example, I could take that 3.0 grams, multiply it by that 14.5%, but as a decimal. That gives you 0.145 as a decimal. And when you write this out, when you do the math, you get 0.44 grams of water were lost. That's what left the compound. So when I asked how much water was in the original sample, 0.44 grams. So out of that 3.0 grams, 0.44 grams of it was water. Now what happened here is you have to pay attention to significant digits. The 3.0 has 2 significant digits. And the way we wrote the percentage, that's 3 significant digits. So you go by the least amount, 3.0. So I wrote my answer with 2 significant digits. That's why it's 0.44. Now, if I want to know how much anhydrous salt remains, well, if I started off with 3 grams of the hydrate, 0.44 grams, or how much water was in there, to figure out how much anhydrous salt remains, all I have to do is the 3.0 grams of the hydrate, subtract out the 0.44 grams of water that was lost, and that will give me how much of the anhydrous salt remains. Now, since we are subtracting here, you go by the least number of decimal places. This one, 3.0, has 1 decimal place. 0.44 has 2 decimal places, so you go by the least number of decimal places when subtracting. So that's 2.6 grams of anhydrous salt. And that's how you can do these problems. There are other variations on how you can do it, but this will cover what you need to do. You have to get the percent composition to figure out how much water is in there. So you can multiply that by the original mass of the sample, and that tells you how much water was in that original sample, how much would be lost when you evaporated it. So that means there would be 2.6 grams in this example of the anhydrous salt remaining.